A highly anticipated return of the Lego videos is brought to you by Pirates of the Caribbean, the main chick in that. I don't know who that is. So, 9-1, we're going to solve systems of equations in two variables. And the most common two variables that are used in this world are x and y in the math world. Now, if other variables are used, we tend to, so like if we used a and b, a would correspond to x and b would correspond to y. If we used E and F, it'd be the same way. In other words, we alphabetize to match which one's X and which one's Y. You'll see why that might actually be important in a second. So let's just kind of get our minds wrapped around what this really means. So let's start with, we run a movie theater and our ticket taker lost the receipts for the Saturday matinee, and pretend that there's no such thing as a computer that will record all that mess. So we only know the total number of seats sold, which happened to be 84, not the number of adult and children tickets separately. So let's come up with a way to express the tickets sold as an equation that relates the number of adult tickets, children tickets, and total tickets sold. Well, let's let adult tickets represent X, let's let child tickets represent Y, and then we know it was just the sum of those two equals our total of 84. Pretty straightforward. Good luck solving that, right? There's infinite solutions to that equation. Oh, whoops, that's what question next is. Is it possible to determine the exact number of adult and child tickets sold for that show? We'd say no. There are multiple solutions. For example, if X was 1, meaning we sold 1 adult ticket, then we sold 83 children tickets. If X was 15, then we sold whatever 84. Let's change that to 14 because that's easier to do in my head. Of course, now that I know it, I should do the other one, but whatever. That means we sold 14 adult and 70 children tickets, etc., right? So then it turns out that the box office collected $570 for that show, and the ticket prices were 10 for adult and 5 for the children's ticket. Let's come up with an equation that relates the total sales. Well, think about it. If we are charging $10 per adult ticket, 10 times X is the amount of money we collected from adults. If we sold Y amounts of children's tickets, 5 times Y is the amount of money we collected for the children, and we know that this sum is supposed to be 570. And again, can we determine the exact number? And we would say no, we cannot. Because this equation is dependent upon the results we get from this, and vice versa. Like if I take this example, this would not work out, right? So we would have 10 times 1 plus 5 times 83. The question is, does that equal 570? And the answer is most certainly not, or I'm super lucky. 83 times 5 turns out to be 415 plus 10. I could have done in my head, but whatever. That's 425, which is not equal to 570. So this doesn't work. That's not a possibility given this information. No, why can't we? We have to solve them simultaneously. Let's say this, a solution in the first equation must also be a solution on the second one. Also be a solution to the second equation. Oh, you can't even see what I'm writing. Good gracious. Hey, there it is. Okay, so let's take a look at what this means, what happens here. So we're going to start with the most basic of systems. We're going to look at two linear systems, which happens to be that example problem we work with. So we know that any linear system has a degree of 1, excluding the case of, say, y equals 1, which is linear. That's this graph, and that has a 0 degree. And then we most often, these graph as a line. We often think about these equations in the form of y equals mx plus b, that's slope-intercept form, or ax plus by equals some value c, that's standard form. There's other forms of it. So we're going to use our past experience with linear graphs and our massive capability for making accurate mathematical generalizations. And what are all the possible outcomes that occur when graphing two linear equations on the same set of axes? Okay, they could intersect, right? How does that look? Something like this. Here's the first one, here's the second one. Bam, that's the solution. Notice it's an ordered pair, an x comma y, that is a solution on both lines. So the intersect option means there is one solution. Okay, let's look at another one. You've heard about parallel lines in a previous life, potentially. And that told you that parallel lines never intersect. Now, maybe ask those of you that are in Alison Price's class, ask her which one it is. Is it spherical or cylindrical? No, spherical or hyperbolic geometry where parallel lines intersect. Also, they intersect at the point of infinity. In this case, there is no intersection, which corresponds to no solution, because it's impossible for a solution on this line to also be a solution on that line. Recall that parallel lines have equal slopes, but different y-intercepts, obviously. Which leads us to the last option. What if the two lines, now this might blow your brains, what if the two lines intersect everywhere? Here's the first line. Here's the second line, right? It's kind of hard to draw this. You're like, what? Aren't they the same line? Yeah, that's it. And what we would say here is infinite intersections, infinite solutions. That means they're the same line. No intersection. I forgot to add that this means parallel. Boy, I suddenly can't spell parallel. Look up how to spell that for me, would you? Okay, so what does the solution for a system of a linear equation look like on a graph, and how can we use our calculator to find it? It is a point in the form of x comma y, and we simply use what we've already been using for our graphical solution methods. We look for the place where the two lines meet. Turns out there are special words for all this. So a system of equations that has at least one solution is referred to as consistent. I had to look these up from your textbook. Any system of equations that has no solution is referred to as inconsistent. I also have to look it up to remember how to spell these. And finally, equations that are distinct from each other. So two distinct equations, they're called independent. And equations that are indistinct from each other, meaning if you graph them, or they're the same, it's impossible to tell the difference. Those are called dependent. All right, so there's the vocabulary.